Yes, good evening, everyone. Uh,
Good evening, sir.
yeah, good evening.
Good evening, sir.
Good evening. People are still joining. Uh, so we'll wait for 1 or 2 minutes.
Yeah, okay, sir.
Okay, let me start. I think the others will join. Okay. So this session is on parallel computing subject. That is elective course MC SE11. Parallel computing. So computing techniques. One is sequential, concurrent, and parallel. So sequential computation, concurrent computation, and parallel computation. So sequential and concurrent computation can be done with only one processor. But parallel computing, if I say, or the simultaneous computing, when I say, we require more than one computing elements or the processors to do that. So in this course, parallel computing course, you're going to study many techniques using which the throughput of the computer system can be enhanced. That is making the computer system to do more work in less time. So that is what is parallel computing is. That is the real need for having the parallel computing. That is, I want to enhance the throughput of my computer system just by adding additional number of processes and simultaneously processing more than one task. So this course is all about that. So you are going to understand many techniques and concepts using which the capability of the computer system can be enhanced so that it performs more computation in less time. Now, in this chapter, beginning, so we are going to understand the state of computing. So the different states of computing, as I already mentioned, sequential computation, concurrent computation, and the parallel computation. And then you understand the multiprocessors and multi-computers, because these are the two parallel architectures using which you can go for dividing a task into among multiple processes and get the work done at a much faster rate. So multiprocessors and multi-computers, these are the two different parallel computer. And then multi-vector and SAMD computer, that is single instruction over multiple data stream computers. So one instruction, but the same instruction performing execution on the multiple data set or the data stream. So these are the things which we'll be seeing for today or looking into. Next, state of the computing, so sequential computing. So sequential computing, all of you are aware of this. So it happens one after the other. If you have written a program, so the statements of the program gets executed one by one, sequentially, one after the other or serially. Now, when I'm performing this computation, sequential computation, now how many processing elements are required for me to do the sequential computation? Now, only one processing element is sufficient. So because, say you have written a program of 10 instructions, now the one processor is required and it will fetch the instruction from the memory, one single instruction from the memory. It performs the execution of it. So there is something called as pipelining, fetches one instruction, decodes the instruction, execute, and writes the result back to the memory. Now, sequential computation is performing one at a time using only one processing element. And in sequential computing, one more thing, what happens when the CPU starts executing one program, so it will continue to execute that program until it gets completed. That means when the CPU is executing the process one or the program one, so in between, if that process is interested in performing some input-output operation, and input-output operation will not be taken care by the CPU, will not be taken care by the CPU. All input-output operations will be performed by a special co-processor called as what IO processor. Now, when IO is handling the input-output operation, CPU, these days CPU will itself involved in performing some other task. But sequential computation, what happens when the CPU is executing some program, and if that program wants to perform some input-output operation, or if it wants to wait for some other operation to get completed, so CPU will also sit idle. That means CPU cannot go and execute some other program. Meanwhile, this program which was currently executing finishes its input-output operation. So that was the kind of execution that happens in the sequential computation. Even the CPU used to sit idle if the program that is currently under execution wants to perform some input-output operation. And next came the concurrent computing. Now, what concurrent computing says is it's a CPU. Say I have 4 processes to execute, all 4 are ready for execution. Now, the process CPU will start executing one program. Now, and say the program, the first program, what the CPU has started executing has 50 instructions in it. So the processor is finished. After executing 10 instructions, the program wants to perform some input-output operation. So now what the CPU will do is CPU will simply switch to the other program which is ready for execution, and it will start executing it. So and it will continue executing the other program until this program finishes its input-output operation. So by the time when this program finishes its input-output time, again the CPU will switch back to this program and continue its execution. Switch back to the first program and continues its execution from the point where it was left earlier. So this is what is concurrent. That means CPU is not going to fully execute one program. It switches from one to the other and resumes the execution of the programs which were left out earlier. So that is what is concurrent computation. So, and next is parallel computing. And again, the number of processing element required for performing even the concurrent computation is also one processing element. One processor is sufficient, and this processor itself is executing the number of programs in a concurrent fashion, or you can also call it as an interleaved fashion. That means why interleaved fashion? Because it performs the execution of some instruction in program 1 and then switches and performs the execution of some instruction in program 2 and again switches back to the program 1 and continues from the point where it was left out, like this. That is what is concurrent. And this switching happens so rapidly, you get a feeling that so the CPU is executing all the programs parallelly. That is what the feeling you get, but the programs are not getting executed parallelly. It is one program what the CPU can execute at a time. But this rapid switching of the CPU from one to the other creates an illusion that the programs are getting executed simultaneously. That is what is concurrent computing. Now, parallel computing is simultaneous computing. Say I have 5 programs with me. I want to perform the simultaneous execution of all the five programs. Then I should have 5 different processing elements. I'll schedule one program on each processing element, and they will be executing simultaneously or parallelly. So now, when compared to sequential computation, concurrent computation, if I compare these two, the throughput of concurrent computation is much faster than compared to sequential. And if you take the parallel computing, again, the throughput of the parallel computing is very higher than compared to sequential or the concurrent, because here you have multiple processing elements involved, and each of them are doing what the task parallelly. These are the state of the computing. Okay. Now what we are focusing is the parallel computing. We get into the topics of the parallel computing. So it is necessary for us to understand the computer development milestones, how the computers are developed. Okay. So the computers, even they started in the year 500 BC. So in the form of before Christ, that is abacus. So the first mechanical computer which was used for calculating, and it had the support for decimal arithmetic operations with carry propagation digit by digit. And after this, Pascal invented the mechanical adder or subtractor in 1642. And then Charles Babbage in 1827, the differential engine. So this is how the computer system, have developed. In 1941, the first binary mechanical computer in Germany. In 1944, the first electromechanical computer came. So prior to 1945, all computers were mechanical computers, and there were no electronic components used in them. Time in the year 1944, so the first electromechanical computer came into. And from 1945 onwards, prior to 1945, we call them as mechanical computer era, and from 1945 onwards, it's called as modern computer era, because the electronic components, started using the electronic components in the computer system. And again, the computers after 1945 till now, so say 2020. So the computers are again grouped into various generations. The modern computers are grouped into different generations, or you can say the computers after 1945 till now, they were grouped into various generations. So first generation, second, third, fourth, and fifth generation. Now, what was the basis for making the computer generations? The computers after 1945 till now, they were grouped into various generations. On what basis these computer generations were made? So these computer generations were made whenever there was a sharp change either in the hardware or the software technologies. So and that sharp change in the hardware and the software technology led to the grouping of computer generations. That means, say, in the next slide, it's there, I'll show you. So first generation, say 1945, so because 1945 is the major year, because here the electromechanical computer started. So 1945 to 54, they were the computer which belonged to this period, they were called as first generation computers. Now, why they were called as first generation? Because there was some kind of hardware and software technology used here. Now, let us look into the hardware technology. So that was there in the year 1945 to 54. So the major components of the computer systems are vacuum tubes. So now these days, the major components of the computer systems are integrated circuits, ICs. So by that time, there were no ICs, integrated circuits were not there. So all were vacuum tubes. The vacuum tubes were there, and then relay memories. And you can, if you want to see how a vacuum tube looks, this vacuum tubes, that time, it was acting as a transistor. So I don't know whether you people have seen the transistor. Transistor has 3 terminals. So now, so that this vacuum tubes were used during 1945 to 54, in the place of the transistor. Now instead of vacuum tubes, we are using the transistors and diodes. So vacuum tubes were the major component. And when it comes to the question of memories, there were relay memories. There were no magnetic memories and there were no semiconductor memories. And what kind of memories were there? Relay memories were there. And CPU was driven by PC and accumulator. So PC, I hope all of you know, because if you studied ALP, you'll be knowing this. PC is program counter. So it's a register which is there inside the CPU, which will hold the address of the next instruction to be executed. And accumulator is another register which holds the data after computation. Now CPU was driven by this. That means PC acts as a guide to the CPU. It is a guide to the CPU. That means it holds the address of the next instruction to be executed and tells CPU what it should do next. And then, so this single CPU, which was available in the first generation computer system and which was driven by PC, so it was capable of performing only fixed point arithmetic operations. It was not capable of performing the floating point arithmetic operations. It was capable of performing only fixed point arithmetic operations. So this is the main highlights of the hardware technology in the first generation computer systems. Vacuum tapes were there, relay memories were there, and CPU was driven by the PC, and there were no special I/O processors also. So these days, all input-output operation will be taken care by the I/O processors. They are also called as co-processors. But first generation computer system, there were no I/O processors. All input-output operation was carried out by the single CPU itself. And what kind of operation it was capable of performing? Only fixed point arithmetic operations, and it was not capable of performing the floating point arithmetic operations. And if you look into the softwares and applications, so these computer systems in 1945 to 54, so they were programmed only using machine or assembly level programming language. So there were no high-level programming languages as we have now. So there was no C programming, no Java programming, all this, and not even COBOL programming also. Nobody uses COBOL these days, and nobody uses Fortran these days. So 1945 to 54, so the kind of programming language was only machine and assembly ALP programs. And how many users it used to support? Only one user. And there was no support for the subroutine linkage. So this was also not available. Subroutine linkage, the function call was not available. And programmed I/O using the CPU. So all input-output operations were programmed to the CPU itself. And the examples, what are the examples? These are all the examples you can give. This ENIAC is a simple calculator, which was used in 1945 to 1954. Now, second generations, again, it goes something like a comparative study now. Now, second generation computer systems, 1955 to 64. So hardware, this is what the hardware technology. So second generation computer, all these vacuum tubes which were there in the first generation computer system, so they're replaced by the transistors and diodes. So all vacuum tubes got replaced by the transistors and diodes, and all the relay memories they got replaced by magnetic core memories. The magnetic core memories started coming, and again all these transistors, diodes, and magnetic core memories. So they were all interconnected using the printed circuit boards. So PCB was used. PCB was used in order to interconnect all these components. But first generation computers, there was no PCB. All these vacuum tubes and relay memories, they were interconnected using the insulated wires. So second generation, so the PCBs came into picture. What kind of PCB again? Only single layered PCBs. And all these transistors, diodes, core memories, they were all interconnected using the printed circuit board. But these days, we have more complicated printed circuit boards, which are multi-layered printed circuit boards. So if it is not possible for you to accommodate all the tracks in one layer, so they go for even placing the tracks layer by layer. They plot a layer of tracks. On top of that, they put layer of insulation. On top of that, So one more layer of tracks, multi-storied tracks, something like this. And this second generation computers, again, there was one single CPU, and this CPU, the capability was enhanced. The CPU was capable of performing even the floating point arithmetic operations as well. Okay, so, but first generation was capable of performing only fixed point arithmetic operation. And now this is capable of performing both fixed point arithmetic operations and as well as floating point arithmetic operations. And special IO processors were also introduced. In the first generation, I told all input-output activity was taken care by the main CPU itself. Now here, so the main CPU is relieved from the burden of doing the input-output activity by adding a special processor called as IO processor. So I can say this IO processor is an assistant to the main processor. All input-output activity will be taken care by this processor. When this processor is performing the input-output activity, the main processor can involve himself in doing some other task. Now, this co-processors were added to increase the throughput. The now co-processor is acting as a assistant to the main processor. And then multiplexed memory access. Actually, now you're able to access more than one memory. Multiplex memory access. Now coming to this hardware and software applications, so high-level languages were used. Few high-level languages, not C programming, not Java programming. In second generation, so there were few high-level programming languages like Algol, COBOL, Pascal. These kind of high-level programming high-level languages were there with their supporting compilers. And then subroutine libraries were also added, but in the first generation, there were no subroutine libraries. And process monitoring, this is. And examples for the second generation computer system, this is IBM 7090, CDC 1604. So, and if you Google them, you will get the picture of all those systems. You can have a look how the systems were looking that time, 1945, 55 to 64. Third generation computer systems, so 1965 to 74. Now, hardware, if we look into the hardware technology, so ICs came into picture. Now all this transistors and diodes, they got replaced by the integrated circuits, because within an integrated circuit, you'll find millions of transistors and diodes. So, and that too, what kind of integrated circuits? Small scale integrated circuits and medium scale integrated circuit. SSI is small scale integrated circuits, and MSI is medium scale integrated circuits. So again, these integrated circuits are grouped into three classifications: small scale integrated circuit, medium scale integrated circuits, and very large scale integrated circuits. In third generation, there were only small scale integrated and medium scale integrated circuits. And on what basis this classification is made? This is purely based on the density of the transistor count. And when I say small scale integrated circuit, you have very less number of transistors density here. And it is expressed in terms of millimeter square. How many transistors you'll find inside in per millimeter square area of an integrated circuit chip. And MSI, if I say, you'll find the transistor density is more, and VLSI, it is very large number of transistors and diodes you'll find per square millimeter area of the integrated chip. Next is multi-programming. The concept of multi-programming also came into picture. Now, till third generation, it was batch processing. Now, that means you're able to load one job into the main memory, and the CPU is to execute that program until its completion. Even if that program wants to perform an input-output operation, it was not possible for the CPU to switch to the other program and execute, because there was only one program loaded into the main memory. And CPU is to sit idle until this process finishes its input-output operation. So from that, the concept of multi-programming came. Now, what is multi-programming? So multi-programming allows several ready jobs or ready processes to be loaded into the main memory. CPU will start executing one process at a time. If that process wants to perform an input-output operation, CPU will not sit idle here. Instead, the CPU will take the next ready job, which is already there in the main memory, and it will continue with its execution. So that is what is the concept of multi-programming. So and this multi-programming it just came to keep the CPU busy always. See, if you want to increase the throughput of the system, you should not let the CPU sit idle even for a single millisecond. If the CPU is active and if it has some work to do all the time, you have to see that CPU gets some work to do all the time. With that, we can enhance the throughput of the system. So the multi-programming OS concept came into picture in the third generation. And then pipelining concepts also. What is pipelining? So pipelining is a concept or a technique, so which is used in order to overlap the instruction execution. Like, for example, you people submit an application form to the IGNOU, and uh, and all of you, so there is a predefined template for filling the form. All of you have filled it, and before submitting, assume the form has 3 sections, 4 sections, 4 important sections. All the 4 important sections needs to be verified by the IGNOU officials before submitting. You take the form and you go to the IGNOU official. If one person or there is only one person sitting at the counter and he wants to verify all the 4 sections, and to taking 1 minute. And for verifying all the 4 sections of one particular student will take 4 minutes. Say in a queue there are 10 students standing. Now for processing the because one section will take 1 minute. Like that, there are 4 sections. So 4 minutes will be taken in order to process the application in form of one student. So 10 students are there in the queue. 4 into 10, 40 minutes he has to spend. Instead of that, I'll make 4 separate counters. So 4 people sitting at 4 different counters. The first person will come to the first person sitting at the counter, and the first person is specialized only to verify the section 1. He'll verify the section and he'll send him to the next person that I'm sitting second counter. The second person is specialized in verifying the section 2. Now when the second person is verifying the section 2 of first person, the first person is simultaneously verifying the first section of the second person. So now 2 things are happening simultaneously. So when the second person in the counter finishes verifying the second section of the first student, he will be sent to the third person, so in the counter, and is specialized to verify the third section. When third person in the counter is verifying the third section of the first person, the second person is verifying, simultaneously verifying the second section of the second student, and the person who is sitting at the first counter will simultaneously be verifying the first section of the third person. Now these three are happening simultaneously. And fourth, a counter, the person who is sitting at the fourth counter, he'll be verifying the fourth section of the first student. Simultaneously, we have the third person sitting at the counter verifying the third section of the second student, and the person who is sitting at the second counter verifying the second section of the third student, and the person who is sitting at the first counter is verifying the first section of the fourth counter. Now all these things, the maximum overlapping possible is 4. Now 4 things are happening simultaneously. Now for the first person to get out of the queue with this 4 counter facility, how many minutes it will take? 4 minutes. For the second person to 4 minutes. For the second person to get out of the queue, so he need not wait, we need not wait for 4 more minutes. Now the second person will get out of the queue in 5th minute. And the third person will get out of the queue from the 6th minute. Only to for the first person to get out of the queue, so 4 minutes I have to wait. And out of 10 students, 1 student has finished its processing in 4 minutes, and the remaining 9 students will be finishing their processing in 9 minutes. So 9 plus 4, 13 minutes. Now all 10 persons are processed in 13 minutes. Now if only single person is doing, now how many minutes? So 40 minutes. You can just compare where is 40 and where is 13. So now what is the speed up of a 4-stage pipeline process or something like this? This is a 4-stage pipeline processor. 4 persons sitting at 4 different counters is the 4-stage pipeline processor, and each one is specialized in doing something. What is the speed of this? Now 40 by 13, you divide it. So 40 by 13, you'll get almost 3, almost 4 times. With the pipeline execution, so the throughput achieved is 4 times more than the non-pipeline processor. So the concept of pipelining also came into picture. here I gave you the example of 4 counters and 4 different people specialized in different section setting. But when I say pipelining here with respect to the processor, so it is instruction fetch is one stage, instruction decode is another stage, execute is one more stage, and write back is another stage. 4-stage pipeline processor. Sometimes they can also have 5-stage pipeline processor, 6-stage pipeline processor also. So this pipelining concept also introduced in the 3rd generation just to enhance the performance of the computer system. Am I audible? Are you people?
Yes, sir.
Yeah. And then the concept of cache memory, also came. So this cache memory, it's used in order to reduce the performance gap that exists between the CPU and the main memory. So CPU is much faster. It can run at much faster than compared to the main memory. And this cache memory sits in between the CPU and the main memory, and just bridges the performance gap that was existing between the CPU and the main memory. So main memory can operate in milliseconds range, but processor can operate in nanoseconds range. There's a lot of performance gap between the processor and the main memory. Hence, the cache memory is used just to bridge that performance gap. So now the cache memory can also operate almost at the rate of what CPU. Or in other words, if I want to give a simple analogy, this cache memory is something like a wallet in your pocket. Say I want to buy something, so I assume I don't have the wallet, I don't have the money, I want to buy something. What is that I have to do? I have to go to the bank, withdraw the money, and then I have to go and purchase. So a bank is something like the main memory. So going to the bank and then going to the shop, buying, it will take more time. Instead of that, what I'll do? So once in 15 days or once in a month, I'll visit the bank. I withdraw the money, which is required for me, and I'll keep it in my wallet. Now, wallet is something like a cache memory. Now, wallet is always available with me in my pocket. I can go to any shop and I can spend it immediately, something like that. So cache memory, is much faster than the main memory, and this is the best choice for bridging the gap between the CPU and the main memory. So you take the data from the memory, fill it into the cache memory, and supply the data from here to the processor. It is much faster than compared to making the CPU directly access the data from the main memory. And concept of lookahead processors were also introduced. So here, when CPU is currently executing one instruction, so this lookahead processor will go for fetching in advance, the next set of instruction, and it does some predictions also. Based on the predictions, it will predict which probable instruction will be requested by the main CPU, and that will be fetched and kept ready for the CPU to execute. And these are all the techniques which are used in order to enhance the performance of the computer system. So next, this is with respect to the hardware technology. Main thing is the ICs, integrated circuits, and then multi-programming OS concept came. And these are all the concepts which were added to the existing architecture of the 2nd generation computer just to maximize its performance. Next, software and applications. Now, multi-programming, as I already told, multi-programming OS came, and along with the time-sharing OS also. So time-sharing OS is, now here in multi-programming, whenever the process which is under execution wants to perform an input-output operation, the CPU will switch to the next process and execute. But in time-sharing OS, the CPU, periodically, it's a time slot is allotted. Say every process is executed only for that time slot period. After that time slot elapses, so the CPU will simply switch to the next process and executes. It happens in a round-robin fashion. Every process, say for example, if there are 10 processes in the main memory, every process will be executed for say 1 millisecond. Now, after the first process is executed for 1 millisecond, CPU will switch to the next process, execute that process for 1 more millisecond, second process, third process, like this 12th process, and again switch back to the first process and performs execution for 1 more millisecond from the point where it was left out. That is what is time sharing OS. And multi-user applications also came into picture. So applications where multiple users can use. So examples are these written here. Next, 4th generation computer systems. In the 3rd generation, it was integrated circuits. What kind of integrated circuits? Small scale integrated circuits and medium scale integrated circuits. The 4th generation, so LSI, large scale integrated circuits and very large scale integrated circuits came into picture. So the again, this classification is mainly based on the transistor density. So now when I say large scale integrated circuits and very large scale integrated circuits, so you can find millions and billions of transistors per square millimeter area of an integrated circuit. I hope all of you have seen the integrated circuit, the small integrated circuits with the pins connected to it, correct? So that is. And semiconductor, all this till third generation magnetic core memories were used. Now in the fourth generation, all this magnetic core memories got replaced by the semiconductor memories. And the fourth generation also saw the emergence of the parallel computer architecture. Till third generation, it was single processor, uniprocessor architecture. In the fourth generation, the parallel computer also came. So parallel computer in the form of multiprocessor and multi-computers, and also vector supercomputers also started emerging. This is with respect to the hardware in the fourth generation computer system. Now coming to the software and applications, multiprocessing processor OS came, because we have now, it's not the single processor architecture, you have multiprocessor architecture. Even now people say I have dual core processor, quad core processor, octa core processor. When you say dual core, how many processors it has? It has 2 processors. When I say quad core, how many processors it has? 4 processors. So to support that, when you have multiple processors, you require multi-processing operating system. And then they're supporting languages. For example, when you have multi-processor, you should write the parallel programs for it. Now in C also you can write parallel programs by using something called as OpenMP. So parallel programming, and their supporting compilers were also developed. And thread programming is also there. Now parallel programming and thread programming, all these things is to take full benefit of the parallel computers like multiprocessors and multi-computers. So what is multiprocessor and multi-computer? There are a lot of differences between these two. I'll tell you at the later slides. So this is about the fourth generation. You can say till now. Now these days we have high density and high speed processors. So and scalable architectures. Correct? No? That means the architectures can be extended to support the increasing demand or the increasing load. Superscalar processors are also available. Now in softwares and application. So till here it was process architectures. Now in fifth generation, till what you call it, instruction level parallelism. So a technique later you understand this thing, instruction level parallelism. So the main focus was on the instruction level parallelism till fourth generation computers. Okay. Now and in the fifth fifth generation, so it is parallel processing. So in the fifth generation computer system, this ILP, instruction level parallelism, got saturated. So all the researchers till fourth generation, they started exploiting with respect to the ILP. They exploited all sorts of ILP to maximize the performances of the computer system by what? Using instruction level parallelism. And by 1991 or very close to 2000, so this ILP got saturated. That means there was nothing left to exploit by the researchers in order to maximize the performance of the computer system. Or let me give you the quantitative analysis. Till 2000, year 2000, the performance of the computer system used to increase by 52% every year. That means the performances of the computer system used to double once in 2 years. Till 2000, the performance growth rate of the computer system was 52% till 2000. And after 2000, what happened? The performance growth rate reduced from 52% to 20%. So the performance improvement of the computer system after 2000 used to increase only by 20%. So because ILP got saturated and there was nothing left to exploit by the researchers, and the researchers just started focusing towards another form of parallelism called as data level parallelism. So now this massively parallel processing architecture focuses more on the data level parallelism. And again, once the researchers started focusing on the data level parallelism, the performance of the computer system again increased from 20% back to 55%, not even 52%, more than that, that is 55%. So, and again, heterogeneous processing. Now, today's world, we say it is a distributed computing world. So, because example is the internet. So we, all of us are connected to the internet. So we are connected to the internet through cell phone. We are connected to the internet through the laptops. We are connected to the internet. Even the cars, are connected to the internet. Even the smart devices which you use in the house are connected to the internet. Even the smart watches are connected to the internet. So like this, the many different heterogeneous devices which are connected to the internet, but still the communication is happening smooth. So, and that heterogeneous processing is possible because of the dependable software or the middleware software is there. What it is doing, it is hiding all the heterogeneity. Now, if I send something, if I send a mail from my Android phone, the same mail across any device you take, whether it may be I'm viewing it in my smartwatch or whether it is viewing it my desktop system with Windows operating system or my desktop system with Linux operating system or with desktop system with Mac operating system. So all these are heterogeneous. We have heterogeneity in both the respect. What are they? In what with respect to hardware also, with respect to software also. Now, all this heterogeneity is successfully masked in middleware software. Now, what is that middleware software is doing? It is doing necessary conversion just to mask the heterogeneity. So that is what the middleware software were also developed just to mask the heterogeneity, because today's computing world is no longer an homogeneous computing world. If I say homogeneous, all the devices which are existing in this world should be of same hardware and same software configuration. So and unfortunately, we don't have the homogeneous world. What we have is an heterogeneous world. So and that heterogeneous processing is also possible because of the middleware software. So now in the fifth generation, the focus is more on this, and that has become a new challenge also, the grand challenge application, because masking this heterogeneity is a challenging application. So we have examples here, and if you know any other processor what you people are using, you can write them also, Intel processors and many things. Till he understood how the computer milestones, how the modern computers have evolved from 1945 till now. So next, what are the elements of the modern computer? So you can look here, the diagram. So the major components of the computer system, it starts from here. We have the hardware architecture, the bare hardware components. On top of that, you have the operating system. Say, if I say there is no operating system, I have only the hardware component. Say I've just brought a new computer system or a new laptop from the shop, and I don't have the OS installed in it. So will I be able to perform the computation? I'm not able to perform any computation because it doesn't have the operating system. Now, what is an operating system? An operating system acts as an intermediary between the computer hardware and the user. Without the operating system, it is not possible for you to perform the required computation. It acts as an intermediary, or in other words, you can say the operating system manages the computer hardware resources. This is operating system is responsible for fairly allocating this computer hardware resources to the processes which are running in the system. It will fairly allocate all the resources here, because when I say system, there will be n number of processes running, and we have usually will be having the limited resources. You cannot have unlimited resources or infinite resources. When I say resources, it is always limited. Now, what operating system does, it knows how to fairly allocate this limited resources to the n number of processes running without causing any conflict or deadlocks. Now, on top of this operating system, we have something called as application software. So this is what you people write. So if I write some program, it is an application software. Now, what is that I'll be doing? In that program, when I'm writing a program, I'll be writing the sequence of instructions in order to tell the operating system how or what kind of resources should be used in order to perform my computation. My application software here, it will inform the operating system, this is what the user is interested in doing. This is the kind of a computation, and to perform this computation, these are all the resources required. And operating system will take the responsibility of allocating all those resources to the user application, and you have your application software getting executed. Next, now this is one side. If you look into the other side, computing problem. Now, how you're going to write an application software? So, application software, to write something, you should have a problem. First, you got to identify the problem statement. What is the problem? And for that problem, using some programming language, whether it may be an assembly level programming language or high level programming languages like COBOL, ALGOL, or still very high level programming languages like Python, Java, C++, or C#. Using them, you write the program and just identify the problem statement, design the algorithms in data structure, because after identifying the problem statement, you got to write the sequence of steps how to solve that problem. That is what is the algorithm. Algorithm is nothing but the sequence of steps. When you're designing the algorithm should be mapped to the hardware architecture, because you're going to utilize these hardware resources effectively. You should not make wasteful usage of these hardware resources. Now, within a computer system, we call three things as the precious resources. One is CPU, memory, and IO. These three resources are considered as the most precious resources of the computer system. The algorithm which you design, it should not make wasteful usage of these resources. Now, the algorithm which you design, it should consume minimum amount of this system resources and it should run. With that, you can also enhance the performance of the computer system. And after your algorithm is designed, next you go for programming it, implementing it using some high-level programming languages, and then you bind, compile, and load it, so it becomes an application software. When you run that, so this in turn talking to the operating system, and operating system understands from the application software what are all the resources required in order to perform this particular computation, and allocates those resources to the application software. Application software performs the computation, and the result is given to the user. So these are the elements of the modern computers. So summarized in this simple diagram. I hope you people are following. I need one response from you people.
Yeah, sir.
Yeah. Is my voice clearly audible, or is it breaking in between?
Yes, sir, it is audible.
Yes, sir, it is audible.
Clear, it's clear. It's
Yeah,
clear.
Yes, sir.
okay. Yeah. Sometimes because of the network issues, sometimes the voice will group breaking. Okay, luckily it's not happened. Okay. Next. Now, evolution of the computer architecture. Computer architecture involves both of the following. That is hardware architecture. The hardware organization also has evolved, and programming wise also, software wise also, it has evolved. Now, initially, the computer architecture was based on this one human architecture. So, one human architecture, the computer system which are based on these architectures are sequential machines. That is what I explained in the very beginning. Three computing states of the computing: sequential computing, concurrent computing, and parallel computing. So, this one human, the computer systems which are based on the one human architecture, they are sequential machine, and they perform the computation sequentially, one after the other, executing the scalar data. That means one instruction can perform execution only on one data. So now these days we have SIMD architectures also. Single instruction performing execution on the multiple data. That is one instruction. You load one instruction into the CPU, and that is capable of performing the execution on multiple data items. Okay, that is. And then look ahead processors, all these things I've already told you. Look ahead processors, third generation, started using the look ahead processors in order to fetch the instruction well in advance. So
Means data there.
yes.
You have mentioned there executing scalar data. What does it mean, scalar data?
Now execute scalar data in the say, for example, I want to add two numbers, A and B.
Okay.
Yeah, two integers it is, adding those two separate integers. That is what scalar. Say, for example, I want to add two arrays.
Okay.
Array is a vector.
Yeah.
Array is a vector. When I want to add, say, for example, array, I have an array A of size 10, array B of size 10. I want to add these two arrays. I'll get a new array. Now, what is the kind of operation you're doing here? Addition.
Addition.
That is the operation. You got to have an addition instruction in the CPU. And how many data? These many data.
Yes, sir.
Now, first, the instruction is same, but it's performing. First, it will perform addition operation on A of 0, B of 0. Next, it will perform A of 1, B of 1. A of 2, multiple data. That is what is vector data. Next is, and these concepts, pipelining, I've already told you. So, parallelism, okay. And then Flynn's classification. This is one more important thing. So, a person by name Flynn, he classified the computer architecture into 4 types. One is SISD. I think let me explain. SISD, if you have pen and paper, you can note down. SISD, single instruction stream over single data stream. The SISD architecture. So this is a typical uniprocessor architecture, which is capable of executing one instruction on one data at a time. So that is what is SISD architecture. Now another one is SIMD, single instruction and multiple data. That is what I told you now. So one instruction operating on multiple data. You just load one instruction, to the CPU, and it's capable of performing it. Say, for example, I have 4 CPUs. I'll load the same instruction on all the 4 CPUs, and each CPU will be operating on different data set. Now, if processor 1 is performing the addition of A of 1 and B of 1, so processor 2 will be performing the addition of A of 2 and B of 2, and processor 3 will be doing the addition of A of 3 and B of 3, like this. Okay, that is a single instruction stream over multiple data stream. And then you have MISD also, multiple instruction on single data. So you have multiple instructions executing on the single data. So for example, so say I have 4 instruction, the data is given as instruction input to the first instruction. What first instruction will do, it will do some processing, that is not the complete result, what you get out of the first instruction. It is an intermediate result, and that intermediate result is given as input to the next instruction, and the second instruction again does some transformation. You get an intermediate result, and that is given as input to the third instruction, and third instruction again does some processing. Output of that is given as input to the fourth instruction, and it does some transformation, fourth also, and the output what you get from the fourth instruction is the final one. This is what is MISD, multiple instructions on single data stream. Data is only one. So the data, the original data, you're giving it as input to the first instruction. Output of the first instruction is given as input to the second instruction. Output of second is given as input to the third, and output of third is given as input to the fourth. The original data is entering, at instruction 1, and the processed, finally fully processed data you're getting out of the instruction 4, and all the data which you see in between is the intermediate result. That is not the final result. That is MISD architecture. That is one more classification which was made by Flynn. And the fourth classification which was made by Flynn is MIMD architecture, multiple instruction or multiple data streams. Instructions are also multiple and data are also multiple. And remember, this MIMD architectures are reserved for the parallel computers. All parallel computers work with this MIMD architecture. So parallel, we'll discuss this. I have the diagram, I'll show you parallel and vector computers later. Okay, next. Now, evolution of computer architecture. This is the layered architecture. Now you have the hardware, addressing space, communication model, and then languages supported, programming environment, applications. Now, one thing you have to understand more here is this mission independent and mission dependent. Now, if I take here, from here, this layer to this layer are mission dependent. So this, is mission independent, and these two layers are in between, languages supported and the communication model. So applications and programming environment is mission independent, Pakka mission independent. That means they can be easily ported from one hardware platform to the another. Now, when I say the hardware architecture, this addressing space, this is the place where your operating system sits. So few cannot be ported easily. Right? So whenever you're developing any application, you have to design it in such a way that it can be easily ported from one hardware architecture to the another hardware architecture. Now, if I say the application which is binded very close to the hardware, then you cannot make it portable, because you got to do a lot of changes in order to port it to and make it execute on a different kind of hardware architecture. If I say the application which I've developed is not confined very tightly to the hardware architecture, and if it is loosely coupled with the architecture, hardware architecture, then I can say it is portable. I can easily make it with minimum changes. I can make it operate on a different kind of hardware architecture also. Now, this is implicit and explicit parallelism. Now here, I have two flow charts here. You can this is depicting the implicit parallelism, and this is depicting the explicit parallelism. Let me focus on this first. So the programmer, they write some program. Now what is writing? Source code written in sequential languages like C++, C or C++, Fortran or Pascal. Now, these are all sequential programming languages. Now these days, even C also supports writing the parallel programming languages. For that, you have to use an additional module called as OpenMP. Using OpenMP, you can go for writing the parallel program. But what I'm saying, C program here is the sequential programming language. So say a programmer has written some C sequential program. Now I'm using a parallelizing compiler now. Now what this parallelizing compiler will do, so the program is written sequentially, it's a sequential program written. This parallelizing compiler will go for identifying the parallelism within the program. So this parallelizing compiler will identify the parallelism. That means the parallelizing compiler will identify how many segments of the program written by the user can be executed parallelly. So that we'll understand later in my topic. There is something called as dependency resolution, a dependency graph, data dependency, resource dependency, all those things it will take into consideration, and then it will identify so the segments of the program which can be scheduled for parallel execution, and then generates a parallel object code and execution by the runtime system. This is the parallel. This says now which segments of the program can be scheduled for parallel execution on multiprocessor system. Now here, if you, this is what is implicit. Now what you're doing is the normal sequential program you're writing, and you're compiling that by using a parallelizing compiler. This compiler will go for detecting the parallelism embedded in a program and then construct the parallel object code. And now this parallel object code can be scheduled for execution on multiple processors. Now here, what you're doing, and the burden here in this implicit parallelism depends heavily on the parallelizing compiler, because you, as a programmer, I write the normal sequential program without worrying much about the parallelism. But this parallelizing compiler, the success, depends on how intelligent the parallelizing compiler is. It should go for identifying the parallelism which is there in your sequential program and build a parallel object code so that it can be scheduled for parallel execution on multiple processors. Now the other side, programmer, what we're doing now the programmer is not writing a sequential program. Instead, we are making the programmer himself write a parallel program, using I said in C, you can write the parallel program by using OpenMP. Similarly, other programming also it's there. In C++, you can use the concept of threads and you can go for writing the parallel programs. This. Now, this compiler, what I'm using, is a concurrency preserving compiler. Now, here we're already returned the concurrent program or the parallel program. Now, the compiler, what I need to do is just preserve whatever the parallelism I have specified. Just preserve that, and concurrent object code is generated and execution by the runtime. Now here, the success depends on the intelligence of the programmer, because how efficiently is writing the parallel program, and the burden is less on the compiler. But here, so less burden on the programmer and more burden on the parallelizing compiler. This is what is explicit parallelism, because the user explicitly writes the parallelism in his program, in his source code. Here, user is not writing any kind of parallelism. What he's writing is only the sequential program, which will be compiled by using a parallelizing compiler. Okay, this is the difference between implicit parallelism and explicit parallelism. Next, this is important. On this topic, you'll get the numerical problems. You'll get the problems to solve. Okay, so system attributes to performance. See, you take any computer system. So the performance of the computer system is dependent on two things. One is mission capability and program behavior. So these are the two factors on which the performance of the computer system is dependent. So the mission capability is nothing but hardware capability. It is dependent. Any computer system you take, so the performance of the computer system is dependent on the hardware capability and the program behavior. How well the program is written and how good the program can execute by consuming the minimum amount of system resources. Say I have two programmers, program 1 and programmer 2. So I ask both the programmers to write the program for the same thing. So the programmer 1 writes a very efficient program, and the programmer 2 does the same job as the program 1, but has written an inefficient program, which consumes too much CPU cycles, memory, and devices. But this doing the same job by consuming minimum CPU. That is what I say. The program written by the programmer 1 behavior is very good than compared to the program written by the programmer 2. Ultimately, they may be offering you the same service, but how they are offering, so behavior wise they're different. So this is consuming less CPU cycles, and this is consuming more CPU cycles, and this is taking less memory, and this is taking more memory, and this is consuming less IO devices, and this is consuming more IO devices. Now, based on that, the performance of any computer system is dependent on these two, so that you can directly say. And apart from that, peak performance also maximize the performance. The peak performance of the computer system is solely dependent on these two things: machine capability and program behavior. Now, how do you measure the program behavior or the machine capability? There is something called as turnaround time. Now, I hope all of you know this turnaround time. What is turnaround time? Time taken by the program, from the compilation till loading, executing, and giving you the final output. Now, when I say compile time, load time, execution time, memory access time, input output time, if you sum all this time, that gives you the turnaround time. When I finally sum all these times, the time what I get, it should be less, very less. If turnaround time is very low, then I say the performance of the system is very good. If the turnaround time is high, very high, then I say the performance of the good is very bad. Sorry, the performance of the system is very bad. So this turnaround time, to some extent, can be used as a metric to say whether the system is good or bad. Now, apart from that, there is something called as cycle time, clock rate, and cycles per instruction. These topics are also important. So what we are going to do now next is we're going to derive and just to find the total time required to execute any given program. So we are going to derive an instruction, and to understand that instruction, all these terms are required. Now, all modern computers, today's computers are driven by the clock cycles. If you want the processor of the today's computer system to do any task, you got to give a bribe. What is that bribe? Clock cycles. So processor will not do if you don't supply the required clock cycles to it. Say, if you want to tell processor fetch an instruction from the memory, you have to give a clock cycle to it. And only when you give a fetch instruction cycle to the CPU, it will go and fetch the instruction from memory. And then after it fetches the instruction from the memory, to tell the CPU decode the instruction, you have to apply one more clock cycle again. So when you apply the decode cycle, processor will decode the instruction. Now, after decoding, for the processor to execute the instruction, you have to apply one more clock cycle that is called as execute cycle. When execute cycle is given to the processor will execute the instruction. Now, after execution is complete, to tell the processor write the result back to the memory, you have to give one more cycle that is called as write back cycle, or simply the write cycle. Now, for a processor to perform any job, it requires what is called as clock cycles. So, or I can say the clock cycles are the bribes that are given to the CPU for it to perform any task. Now you understood clock cycles are necessary for the processor. Now, if I ask you a question, so clock cycles are necessary for the processor. Does the processor have the ability to generate the clock on its own? No, processor doesn't have the ability to generate the clock on its own. Now, how do the processor get the clock cycles? So clock cycles to the processors are supplied from an external circuitry called as oscillator circuit. There is an oscillator circuit, separate circuitry, and that circuitry will supply all the clocking requirement of the processor. And again, in that oscillator circuit, there is something called as a quartz crystal. It's a crystal. If you have observed the printed circuit boards, and the printed circuit boards with a small microcontroller, so you might have seen the crystal, quartz crystal. On top of that, it will the frequency will be written 12 megahertz quartz crystal, or 16 megahertz quartz crystal, 64 megahertz quartz crystal, something like this. Now, inside the oscillator, there is a crystal called as quartz. And this is the one which is responsible for generating the clock cycle. What this quartz crystal will do, it will oscillate with a well-defined frequency. Now, what kind of, you can just imagine with the pendulum clock. So if you have the wall clock with a pendulum, pendulum, what it does, it oscillates. It starts and then it goes back. Now let me switch on my video, so that I can wave it and show you. Yeah, hello.
Yeah, we can see. Yeah, we can see you.
Yeah. Now the quartz crystal, what it will do is with a very different frequency. Now what is oscillation? See, if you are seeing the pendulum, it will be oscillating. It starts from here, goes till here, and comes back. This is one cycle or one oscillation. So starting from this point, going here, this is off cycle completed by the pendulum. Go back. This is a off cycle. So one cycle. If it comes back to the original position, we call it as one cycle. Correct? So that is what is the quartz crystal. It oscillates with a very different frequency. Say, for example, a quartz crystal, if it is 16 megahertz, what it will do? It will oscillate 16 into 10 raised to 3. It will complete 16. So many. Sorry, 1 second. The process 3 gigahertz, 4 gigahertz, you see. You can just imagine, the quartz crystal which are how many times it oscillates? 4 giga times per second. So big. Now, what oscillates the frequency? Cycle time is the time you can buy what
Your voice is not clear, sir.
starting from here. System time by what that is what called as cycle time. So I say 16 megahertz what now turn around and what is understood? Audible? Yes, please do respond. Hello.
16 raised to 16 into 10 to the power of 3 tasks is done in 1 second. Yes, sir.
Yes,
Am
sir.
I audible now? Am I audible now?
Yes, sir. You're audible, sir.
Okay. Now
Yes, sir.
that is,
Now it
if I
is clear.
say, if I say quartz crystal is of frequency 16 megahertz, so 16 into 10 raised to 6. Mega is nothing but 6. 16 into 10 raised to 6. So many oscillations it can do per second. Now, what is cycle time is the time taken by the quartz crystal to perform one such oscillation is called as cycle time. What is the time taken by the quartz crystal to perform one oscillation? That one cycle or one oscillation. That is what is the cycle time. Now, clock rate. Clock rate is how many such oscillations it can do per second. Now, if I say 16 megahertz quartz crystal, how many oscillations it is doing per second? 16 into 10 raised to 6. That 16 megahertz itself is the clock rate. Now, unit for this cycle time is nanoseconds. Usually, the cycle time is measured in terms of nanoseconds, and clock rate is measured in the frequency is hertz. The unit for frequency is hertz. The clock rate is measured in terms of megahertz. Now, this quartz crystal, 16 megahertz, if I say how many oscillation, what is the clock rate? 16 into 10 raised to 6 oscillations per second it will do. And then cycles per instruction is another important term. Now, I told instruction, execution. say it requires to tell the CPU to perform the execution of one instruction, I told you have to supply 4 cycles. One is fetch cycle, decode cycle, execute cycle, and write back cycle. Now, what is the cycle is? That means for the processor to finish executing one instruction, how many times the quartz crystal should oscillate? 4 times. If it oscillates 4 times, how many clock cycles are done? 4 clock cycles are done. Similarly, now the cycles per instruction. Now, how many such clock cycles are required for completing the execution of one instruction? Now I told 4. So because fetch one cycle, decode another cycle, execute one more cycle, write back one more cycle. 4 cycles are required for completing the execution of one instruction. But in reality, that is not 4. Why? Because when you're writing a program is a mixture of instruction type. So because when you're writing a program, you'll be having the arithmetic instructions in your program, you'll be having the logical instructions in your program, you'll be having the branch instructions in your program, you'll be having memory access, memory reference instructions in your program, and you cannot expect all these instructions to take the same number of clock cycles. Hope you're following. Are you with me? Hello?
Sir. Yes, sir.
We are listening, yeah. Go ahead.
All instructions. Program generally when you write, you're not going to write the program by using only one type of instruction. So you're not going to write the program by only using arithmetic instruction, addition, subtraction, multiplication. These are the arithmetic instruction. And when I say program, you'll be using arithmetic instruction, addition, subtraction, multiplication instructions will be there, logical instructions will be there, ANDing, ORing will be there, correct, right? And then branch instructions will be there. So branching from here to there, there to here, branching instructions will be there, memory reference instructions will be there, and you cannot expect all the instructions to take the same number of clock cycles. Arithmetic instruction take 4 clock cycles to execute. Logical instructions are much faster instructions as compared to any other instruction. You compare with arithmetic, you compare with memory reference, you compare with branch instruction. Logical instructions are much faster always. That means they execute in less number of clock cycles. So if I say arithmetic, say, let me take an example, simple example. I've written a program with 10 instruction. Now among these 10 instruction, let me assume 4 instructions are arithmetic instructions. 4 instructions are logical instructions, and 2 instructions are memory reference instruction. Out of this 10 instruction, 4 I'm assuming arithmetic, 4 I'm assuming logical, and 2 I'm assuming memory references. Now this to execute one arithmetic instruction, let me assume I require 4 clock cycle, and to execute one logical instruction, let me assume I require only 1 clock cycle, and to execute one memory reference instruction, let me assume it requires 5 clock cycle. Now 4 arithmetic instructions I have, and to perform the execution of each arithmetic instruction, I have told 4 cycles are required. 4 into 4 is how much? 16 clock cycles are required for completing the execution of 4 arithmetic instruction, and 4 clock cycles are required for completing the execution of 4 logical instruction, because I'm assuming to perform the execution of one logical instruction, I require only 1 clock cycle. So 1 into 4, 4 plus 16, 20 clock cycles, and the remaining 2 instructions I'm assuming memory reference instruction. Usually memory reference instruction, they take more clock cycle than compared to arithmetic and logical. I'm assuming 5 clock cycle here, and 2 such instructions I have. 5 into 2, 10. So totally 30 clock cycles are required. That means the quartz crystal should oscillate how many times? 30 times to complete the execution of my program with 10 instructions. Now 30 is the total number of clock cycles. Now if I want to find what is the cycles per instruction, to on an average to complete the execution of one instruction, how many clock cycles it is taking, total number of clock cycles divided by total number of instruction. Cycles here, 30 clock cycles I got, divided by how many instructions the program has? 10 instruction. 30 by 10, how much I got? 3. So that 3 is the CPI, cycles on an average. Generally, so CPI is written as average CPI. On an average, to complete the execution of my program with 10 instruction, having 3 different instruction types, arithmetic instruction, logical instruction, and 2 memory reference instruction, I require how many clock cycles? 3 clock cycle. That is the average CPI. Now, if I want to say what is the CPI of only arithmetic instruction, it is 4. What is the CPI of logical instruction? It is 1. What is the CPI of what memory reference instruction, it has 5. But collectively, for the entire program, when I'm saying it is average CPI, and average CPI for this program is how much? 3 cycles. That is 30 by 3. Okay. So I hope you understood here. Let me go to the next thing. I have the equations. I'll show you. So this is a performance factor. Instruction count. I'll show all these things. These are all called as performance factor. Why they're called as performance factor? I'll show you in the equation because it is there. And system attributes. All these performance factors are dependent on this system attributes. I have a table. I'll relate in that table, and okay, and we're going to write the equations for all these things right now. So Mips rate, that million instructions per second rating, floating point operations per second, and throughput rate. Okay. Now here, next slide. Yeah, here. Observe now, cycle time. This is what I told. It is denoted by, this is called as tau. The time taken by the quartz crystal to perform one oscillation is tau, and clock rate is the number of such oscillations made by the quartz crystal per second. It is denoted by F, frequency. Now, and these two are related. Tau and F are related. So how they are related? They are related inversely. F is equal to 1 by 2. 1 by 2. Now, what will happen? See, the frequency, if tau decreases, the time taken by the quartz crystal to perform one oscillation decreases, what will happen to the clock rate? Increases. That is what is inverse relation. If one decreases, the other one will increase. Correct? No? If the time taken by the quartz crystal to perform one oscillation decreases, what will happen to the frequency? Increases. That means the number of oscillations made by the quartz crystal per second will increase. And similarly, if the other decreases, increases, the time taken by the quartz crystal to perform one oscillation increases, what will happen to the frequency? Decreases. The number of oscillations made by it will decrease. An average number of cycles per second, that is CPI, I've told you. Now, always CPI, you have to write average because the program is a mixture of instruction type. It will be having variety of instruction types. Hence, you got to write always average. How to find the average CPI? First, you got to find the total number of clock cycles required for executing the whole program divided by number of instructions in that program. That is what I did in the previous example, which I told you, 30 by 10. I got average CPI as 3. Number of instructions in the program, let us denote it by IC. IC says the total number of instructions in the program. Now, the total time required to complete the execution of a program with IC number of instructions can be given by this equation. T is equal to IC into CPI into tau. What is T? IC is the total number of instructions in your program. What is CPI? Average number of clock cycle required to execute one instruction. And what is tau? One cycle time. Now, forget tau for time being. Forget this tau for time being. Take only these two into account. This is giving total number of instruction. And what CPI is saying? Average number of cycles required to complete the execution of one instruction. Now, in my previous example, which I told, what was the value of IC? 10. Now, what is the CPI? 3. 10 into 3 is how much? 30. What is this 30 you got? 30 is not the time. 30 is the clock cycles. So many clock cycles are required to complete the execution of your program with 10 instructions. 30 clock cycles are required. Now, I don't want to say it in terms of clock cycle. I want to convert it into time. What does I have to do now? How to convert this 30 clock cycles into time? I got to multiply it by one cycle time. If you know what is the time taken by the quartz crystal to perform one oscillation, that one oscillation time, you got to multiply with 30. If you multiply this 30 cycles with one oscillation time, you'll get the CPU time. Say, for example, this 30 cycles are there. Assume the quartz crystal is taking 1 second to perform one oscillation. Correct? So in 1 second, it will do 16 into 10 raised to 6 oscillation. So this is just an example I'm taking. Assume the quartz crystal takes 1 second to complete one oscillation. Now, and how many such oscillations the quartz crystal should do in order to complete the execution of my program with 10 instruction? 30 oscillations. 30 into 1. Now I got how much? 30 seconds. It is 30 seconds. But this tau, it is in terms of nanoseconds. You'll get it in terms of nanoseconds. That is 10 nano means 10 raised to minus 9. So so many seconds. Okay. Now memory cycle time. So memory access time, say K is the total number of memory. Till here you understand. I hope all of you understood this equation. T is equal to IC into CPI into tau.
Yes, sir.
Yeah. Now memory cycle. Yeah, K into tau it is written. Now K is the total number of memory references. Okay. And tau is the cycles per, time taken for one memory cycle. Now if you multiply these two, you get the total number of cycle required to access one memory. And P, let me assume it denotes the processor cycle, and the number of cycles needed as M. Okay. Now this CPI now can be expanded like this. Now the CPI can be divided into two things: processor cycle plus memory cycle. Now P is the processor cycle and M into K is the memory cycle. So where M is the total number of memory references, cycles needed, and K indicates how many such memory references are required. Now CPI, when I say, so the average cycle, say for example 3 you got in the previous example, and that 3 includes the CPU cycle plus memory cycles. So that is what is the further expansion of this instruction is something like this, where CPI is a combination of both processor cycle plus, I can tell you why it is a combination of both processor and memory cycle. Now, the instruction execution, I told instruction fetch, decode, execute, and write back. Now, among these three, instruction fetch, what it does, fetching the instruction from memory. Now, what cycle it requires? Memory cycle. Instruction decode, it requires processor cycle. Instruction execution, processor cycle. Write back, write result, it requires memory cycle. Among the 4 stages of the instruction execution, 2 stages require processor cycle and 2 stages require memory cycle. That is, instruction execution and decode requires the processor cycle. Instruction fetch and write result require memory cycle. So that is what it is explained. Again, CPI is divided into the 2 things. This is processor cycle and this is memory cycle. So processor cycle is denoted by P and memory cycle is denoted by M into K, where M is the number of cycles needed per memory reference and K is the total number of memory references made. And so this can be written like this also. Now, so Mips rating is like this. Now, from this equation, you can find always tau. What is one cycle time? You can always find. So tau is equal to, so IC by CPI into, T by IC into CPI. Here. Now tau is equal to IC by T into 10 raised to 6. This is equal to, now IC by T can be written as F by CPI. From this equation, you can know IC by T is equal to F by CPI into 10 raised to 6. Because this tau can also be written as what? 1 by F. So if I'm removing this, it is IC into CPI by F, because F is equal to 1 by tau or tau is equal to 1 by F, because they are inversely related. So I can write this F is equal to 1 by tau, or let me open the notepad and show you. I'll just write here. So observe my notepad. Now F is equal to 1 divided by tau symbol I don't have. I'll just write it as T, and T, tau is equal to 1 divided by F. They are inversely related. Both are true. So if you know F, you can find T, or if you know T, you can find F. Now here, in the next slide, let me go to the next slide. Yeah. Here. Now tau is equal to IC by T into 10 raised to 6. It is not 106, 10 raised to 6. That is what is the Mips rating. Mips rating is written like this. Now IC by T, can be replaced by F by CPI. So now we have the equation T is equal to IC into CPI into small t. Now this T can also be written as T is equal to IC into CPI. This whole thing, instead of that small t or tau, I can write it as 1 by F, like this. T is nothing but what? 1 by F. T is equal to 1 by F. This is also correct. Now from this equation, now IC by T, if I write, IC by T, if I take this IC here, IC divided by big T is equal to F divided by CPI. So from this equation, now IC by T is equal to F. That is the reason IC by T is replaced by F by CPI. And again, this the CPI can be replaced by IC by C. So because CPI is equal to what? Cycles per instruction is equal to total clock cycles divided by IC. So this big C is representing the total number of clock cycles. In the previous example which I took, 30 clock cycles I got. So that is the total number of clock cycle, and this is the total number of instruction. So 30 by 10. So CPI we got was 3. Now this, you know, I can write like this. Now 1 by CPI, sorry, 1 by CPI is equal to, if CPI is equal to this, what is 1 by CPI? 1 by CPI is equal to IC by Ulta, IC by big C. That is what I've written. In the place of the CPI, I've written as F into, in the place of the CPI, IC by C into 10 raised to 6. And similarly, the throughput rate. So the amount of work done per unit time rate, WP, is given by this equation. Mips into 10 raised to 6 by IC. And again, this can be replaced by F by CPI into IC. This is all the mathematical equations are applying. I hope you people understood with this. Understood? Hello?
Yes, sir.
Yeah, with this notepad, what I wrote, I think you people understood. So writing one in the other form, that's all. That's all. Okay. Now next, I have a numerical on this. Let me go. Just read this statement. Read this problem. A benchmark program contains 45,000 arithmetic instruction. That means you have a program. A program is given to you, and that program contains how many arithmetic instruction? 45,000 arithmetic instructions it has. 32. So 32. Sorry. This is 4,50,000. Sorry, not 45,000. 4,50,000 arithmetic instructions are there, and 3,20,000 data transfer instructions are there, and 2,30,000 control transfer instructions are there. That means the program given to you has 3 types of instruction: arithmetic instruction, data transfer instruction, and control transfer instruction. And the count is also given, and it's here. Now continue. Each arithmetic instruction, so each this arithmetic instruction takes 1 clock cycle to execute, whereas each data transfer and control transfer, so assuming is telling, takes 2 clock cycle to execute. So each of this arithmetic instruction is taking 1 clock cycle to execute, and this data transfer and control transfer instruction, they're taking 2 clock cycle to execute on a 400 megahertz processor. What is the clock frequency of the processor? 400 megahertz processor. Determine, you got to do this. So find, determine the effective number of effective CPI or average CPI, one and the same. And then you got to find the Mips rate using this formula. And then the total execution time of this program. What is equation using this equation? Now we'll try to solve this. Now to solve, I will use the notepad again. I'll erase. Let it be there as it is. Okay. Enter. Now, so the problem says, look here. This side, upward. I'll keep it. I'll keep it. Now, so the problem says, now we have how many types of instruction? 3 types of instruction. Now, one is arithmetic. Let me write it as AI. Arithmetic instructions, how many are there? 4,50,000. And then DT, data transfer instructions, how many are there? 3,20,000 instruction. And how many CT, control transfer, let me call it as CT, control transfer instructions are there? 2,30,000. 30,000. And he has also given to perform the execution of each integer arithmetic instruction. How many clock cycles are required? 1 clock cycle. Now multiply. I got to multiply 1 into 1. That is equal to how much it is? 4,50,000 itself. So CC, clock cycle. To complete the execution of all arithmetic instruction, all 4,50,000 arithmetic instructions, how many clock cycles are required? 4,50,000. CC is nothing but clock cycle. So many clock cycles are required. Hope you understood. Now, similarly, to complete the execution of one data transfer instruction, it says 2 clock cycles are required into 2. That is equal to, so it is 6,40,000 clock cycles are required. Correct now? And similarly, to complete the execution of all the control transfer instruction, each control transfer instruction, 2 clock cycles are required. And to complete the execution of all of them, you require 460,000 clock cycles. So for one more 0, so many clock cycles are required. So now I have to find the total. So this is the clock cycle required to complete the execution of 4,50,000 arithmetic instructions. This is the clock cycle count required for completing the execution of data transfer. This is the clock cycle required for completing the execution of CT. Now, if I want to complete the execution of the entire program, how many clock cycles are required? I have to sum all these things. Now, what is the sum of all these things? I have 0, 0, 0, 0, 0, 4 zeros, 4 zeros, and then this is 10, 15, 5, 1 carry 10, 15. So it is 15 lakh 50,000. So many clock cycles are required to complete the execution of the entire program. 15 lakh 50,000 times the quartz crystal should oscillate. So many oscillations are required. Now, okay, this is what the total number of clock cycle, or I can write it as C, big C. Total number of clock cycle required to complete the execution of my entire program is 15 lakh 50,000 clock cycles are required. Now, he has also told you that, so this 40 megahertz, what is this 40 megahertz? F is given. F is equal to, so 400, not 40, 400 mega. So 400 megahertz. This is the clock frequency, correct? 400 megahertz. Now, what you are supposed to compute? Find the effective number of clock cycles per instruction, CPI, correct? No? Now, average AVG CPI is equal to, what is that you have to do? It is big C divided by IC. That is equal to, what is big C? We have just now computed. It is 15 lakh 50,000 divided by IC. What is the total number of instructions? All these things you have to sum again. IC is equal to this one. Let me write 4 zeros, 1, 2, 3, 4, and this is 7 plus 3, 10, 0, 1 carry, 5, 8, 10. Now we have 10 lakh instructions. Now total 10 lakh instructions are there, and to execute this 10 lakh instructions, you require 15 lakh 50,000 clock cycles. Now, if I divide it by 10 lakh, now what is the answer you got? How much you'll get? 55. Correct, huh? 1.55 cycles. 1.55
cycles
per instruction. Unit is also important. So this 15 lakh 50,000 was telling you the total number of clock cycle, and this is telling you on an average to complete the execution of one instruction, how many clock cycles you require? 1.55 clock cycles per instruction. Now right? Now average CPI, we have found it. How much it is? 1.55 cycles per instruction. Next, what we have to do? We have to find the Mips rate. Now you know CPI, average CPI, you know, F, you know. Now you can just find out which equation you can use from here. Now Mips rate, it can be found by using this equation or by using this or by using this. Now you know T you don't know yet. IC you know. Now I'll not use this. F you know. Yeah, CPI you know. This you can use. Correct, no? Using this you can find it. F you know, that is 400 into 10 raised to 6, and CPI you know, that is 1.55. Simplify, you'll get the answer. Now I'll not simplify now yet. Correct, no? So that is what you can do. You can substitute to this. And similarly, you got to find the other thing, what it is. Execution time for this program. Now execution time for this program can be found by using this. T you know, sorry, this is what you have to find. IC you know, CPI you know, tau you don't know, but tau can be replaced by what? 1 by F. IC into CPI by F. Okay, F you know, 400 into 10 raised to 6. You simplify, you'll get the answer. Okay. Yeah, you solve it later. Solve it later. Okay. So that was the problem 1. Now I have another problem also. Just go through this. In a similar way, you can do this also. So try to do this. So only the instruction counts are different and clock cycle counts are different. And 40 megahertz processor is given here. It is not 400 megahertz, 40 megahertz processor is given. So same thing you have to do. You have to compute the average or effective CPI, Mips rate you have to compute, and execution time for this program. Same way as I showed you in the previous for the previous problem, you have to do this also. Just take 2 to 3 minutes of time and solve and tell me the answer. You can find the total number of instructions here. Total number of 45,000 plus 32 plus 15 plus 8. I think it will come to 1 lakh. 1 lakh total instructions here. So multiply and find out the total number of clock cycle. So 45,000 into 1 plus 32,000 into 2 plus 8,000 into 2. So what is the total number of clock cycles?
55,000.
1 lakh 55,000. 1 lakh 55,000 clock cycles you got. Correct, right?
Yes.
Yeah. And divide that 1 lakh 55. That is the total number of clock cycle. Divide by what? Total number of instruction. 125 cycles per instruction you got, and substitute the values to find the Mips rating and execution time. Formulas I'll show you. Yeah, Mips rating formula and execution time formula. You know, T is equal to IC into CPI into tau. If you don't know IC into CPI by it, that's all.
MIPS rate is coming to 25.81.
Which one?
MIPS rate.
Mips rate. Into 10 raised to something is there, let's say.
No, F's value is 40 into 10 raised 6, right? Or 10 raised minus 6.
40 into 10 raised to 6 by CPI is 1.55 into 10 raised to 6.
So that got cancelled. So
Okay.
40 divided by 1.55 is 25.81.
Okay. That is fine. Now, so that means 25 point. How much you got?
25.81.
Yeah, 25.81 million instructions per second it can execute. Per second, it can execute so many. Now, find the time taken to execute that program. 1 lakh into 1.55 divided by 40 into 10 raised to 6.
So can you show the formula for time calculation? I didn't get it.
Yeah, this one is equal to IC into CPI by F u. 1 lakh into 1.55 divided by 40 into 10 raised to 6. I can do here only. I'll just take the lakh. 1 lakh into 1.55 this 1 lakh into 1.55 equal to this divided 6 zeros. 40 0 1 2 3 4 5 6 equal to so many seconds. 0.003875 seconds. If you want to tell this in terms of milliseconds, if you shift the point to this side, Kreno, so 3.8 milliseconds. It will take 3.8 milliseconds.
I'm not able to hear your voice.
Yeah, I did the calculation here in the calculator. I hope you observed it. Correct, no?
Sir, if we follow the CPU time formula, for IC's value it is 1 lakh.
1 lakh.
CPU
I'll do here. Just observe here. Is this 1 lakh? Correct, no?
Yes. Yes, sir.
What is this point? 55.
1.55.
Correct. Is equal to this is what I got. Correct? Now that has to be divided by F. Because you know F. divided by how much is 40 into 10 raised to 6, 40 megahertz, correct? No?
Yes.
40. No. 40. I cannot write here. Karana, what I'll do is 40 followed by how many zeros? Mega means 6, correct? No? 40 followed by 6 zeros I have to put. 1, 2, 3, 4, 5, 6 is equal to. This is the
Okay.
8. Shift. So 8 milliseconds.
For tO's value, we can directly take Mips rate, right? tO and Mips rate. Am I audible? Hello. Hello. For tO's value,
Hello.
we can take Mips rate, right?
Yes, yeah, you are audible. Yeah, you are audible. Tell. For what you are taking? No, use this
Yeah,
equation. It
into
is simple.
tO is there. So
The
for
Mips you have
that,
computed, leave it. Is equal to IC into IF instead of. No, tau can be written as 1 by F. No. Getting my point? This is what. This is what. T, tau, I can write as 1 by F. If I'm applying. Now, if you want tau itself, you take the inverse of 40 into 10 raised to 6. 1 by 40 into 10 raised to 6 you'll get tau. Because tau is equal to what? 1 divided by 40 10 raised to 6 if you do, you'll get tau and put that here. Both the ways it is same. I'm using this now.
but the Mips rate we calculated, its value was different from 1 by F. Or is it different Mips rate and tau? Like, I'm confused between the two.
No. Mips rate, you cannot compare that with the frequency. Mips rate you cannot compare with the frequency.
Okay.
Don't compare that. The Mips rate you got some 25.81, no? That's it. Leave it there only.
Okay.
Now you got to separately compute what? The T. For T, computing T, you are using this equation.
Okay.
Is that clear? It's
Yes,
simple. And then you don't have to complicate it. It's simple. Done? So this is IC is 1 lakh. The CPI is 1.55. I multiply them together. I got 1,55,000. Correct, right? 1,55,000. And you divided that by 40 into 10 raised to 6. Now this is the answer what we're getting. 0.003875. So milliseconds it is taking. Correct now?
Yeah, got it.
We'll go to the next. I think I have one more. So this is the one which we solved first. This was the second one. This is the third one. Now let me highlight this. Here it says the program, the object code has 2 lakh instructions. So many instructions are available. And again, the processor taken is 40 megahertz processor. So the processor what we are considering here is 440 megahertz. So you can just imagine the processors now what we use is 2 gigahertz, 3 or 4 gigahertz speed. Capable of executing this program at 1 lakh instruction in 0.0038 seconds. You can just imagine the processor with 2 gigahertz or 3 gigahertz speed, how much fast it can execute. Now, this program is same as the earlier one. Only thing is the instruction mix is given in terms of percentage. Now, it says arithmetic and logic to execute each. One is the CPI, and instruction, how many are there? 60%. You got to find out what is 60% of 2 lakh. Are you following?
Sir.
This is given in terms of percentage. That's all, and the rest all remain same. You got to find out what is 18% of 2 lakh. You got to find out what is 2% of 12% of 2 lakh. What is 10% of 2 lakh? You'll be getting the count of each of these individual type of instruction, and the remaining steps are same as you solved for the previous two examples. Correct? Will you be able to do it?
Yes, sir.
Yes, sir.
Right. Now you got to find the CPI again, and I think what to find is not here. Just find out the CPI, average CPI, Mips rating, and total time required to execute the program. Because that part is missing here. What to find is missing. So what you have to find, those are the three things again. Just make an attempt to solve this quickly. What is 60?
1,20,000.
1,20,000 arithmetic and logic instructions are there. What is 18% of 2 lakh?
36,000.
36,000 load and store. What is 12% of 2 lakh?
24,000.
24,000 branch instructions are there. What is 10% of 2 lakh?
20,000.
20,000 memory reference instructions are there. Now you multiply 1 lakh to 1,20,000 with 1, and I think next one is 36,000. 36 into 2, and next one is 24,000. 24,000 into 8, and 20,000 into 24,000 into 4, and 20,000 into 8, and find the total number of clock cycles. Arithmetic and logic, you got it as 1,20,000, and then
78,000.
total number of clock cycles you're saying?
And what I have multiplied, sir. First one is 1,20,000.
Yeah.
78,000.
Okay.
6,000.
32,000 it will be. 2 into 36,000.
2,000 for second one.
Second one. Okay. 22. Third one.
96,000.
96,000.
96,000. And then memory.
60,000.
1,60,000.
Now, if you sum all these things,
4,12,000, I guess.
how much?
4,12,000.
4,12,000. Huh?
20. 29. 4,48,000, sir.
4,48,000. Okay. 8,000. So this is what we got. So many clock cycles. We got to divide this by 2 lakh.
2.24.
Yeah, 2.24 cycles per instruction. So On an average, you require 2.24 cycles per instruction. This is the average CPI. Next, you can find out T. T is equal to, so 2 lakh instructions. 2 lakh instructions into 2.24, and again the clock frequency is given as 40 megahertz divided by 4 0 followed by 6 zeros. 1 2 3 4 5 6. So you can simplify this. 2 lakh into 2.24 divided by 40
0
56
0.0112.
0.0112. So this is taking little more time. Why? Because 2 lakh instructions you have, and that was only one. The previous example was only 1 lakh instruction. Right? So that was 0.03. 0.003. Now this is 0.01 seconds.
Again, for this we need to convert as 1.12 milliseconds.
Yeah. No, it is not 1.12 milliseconds. It is 11.2 milliseconds.
Okay, 11.2.
Because 3 you have to shift here. This point should come here. 3 times you are doing 11.2 milliseconds. It will become. So this is equal to 11.2 milliseconds. 11.2 into 10 raised to minus 3 seconds.
Okay.
I think we have. So sorry. This for this I add the solution. The same thing. Yeah. 1 into 60. 60% of it is 2 lakh is 1,20,000. 18% 72,000. 12% 96,000. 10% is this, and total number of clock cycle 4,48,000. Now CPI is big C by IC, that is 4,48,000 by 2 lakh, so 2.24 you got. Now Mips rating, so we have to get this. I don't know if you have computed, so 17.86, and I have not the total time. Total time we computed just now, 11.2 milliseconds. Okay. Now this table, yes, all of you mute. Let me explain this one table and stop for today. System attributes to performance. Observe. Now I see you understood. Say if I want to enhance the performance of my computer system, increase the performance of my computer system, what is that I need to do? I have to reduce IC. I have to reduce the instruction count. Why I have to reduce this equation? See, if I reduce IC, what will happen to T? T will reduce. If T is reduced, time taken to execute the program is reduced, the performance of the computer system is enhanced. Correct? No? That is what. It goes with that analogy. Now, instruction count I need to reduce. To reduce the instruction count, and which system attribute I need to work? Instruction set architecture of the computer. So every programming language has its own instruction set. You know? You got to work with this. If you have very good instruction set architecture, you know, so then IC can be reduced. Next, you can again enhance the reducing what the processor cycle consumes. Here I'll show you. See this. The CPI I split into two components: processor cycle plus memory cycle. Again, by reducing P, the number of processor cycle required, you can reduce T, and with that you can enhance the performance of the computer system. Now to reduce P, what is that I have to do? To reduce P, again, you got to what? Improve the instruction set architecture of the programming language. And next, okay, this is not, wherever check mark is there, I'll just discuss. Now instruction set, again, the compiler technology also. IC can be reduced by using a very good compiler technology. And processor cycles can also be reduced by using the very good compiler technology. And memory, the number of memory references made can also be reduced by using a very good compiler technology. And then processor cycles, using processor implementation technology, what you can reduce is only the processor cycle. You cannot reduce this, and you cannot reduce memory. Yeah, using processor tau also you can reduce, and then cache memory and memory hierarchy, so you can reduce this both processor cycle and the memory access latency. Now, if you want to enhance the performance of the computer system, these are the system attributes on which you need to work. You got to do research on these attributes and then see something can be improved just to enhance the performance of the computer system. So this is how these are the performance factors, and these are the system attributes, and all these performance factors are dependent on this system attributes. So this is how it is. Yeah, let me stop here. And I think the parallel computing, again, it is on 9th of this month. Tomorrow we have advanced internet technology class, again from 10 to 12. We'll meet again there. And that video, it's still generating. The moment it is generated and ready, I'll share with all you people. The morning video. Again, this session video also, the moment it is generated and ready, I'll be sharing with you people.
So at least
Yeah, fine, sir.
Yes, PPT also we need.
Yeah, PPT also I'll share. Yeah.
PPT
Really.
Harish, before winding up, I'm having a question actually.
Yes.
So, see, actually, this is nothing related to this session. So, this is all about submission of the assignments actually. So, there is a limitation for the transfer of to Google Mail to 25 MB only. But what all we have generated the PPT, even in the compressed form also, it is something around 50 MB. So we are not able to transfer that. What would be the alternative way that we can submit our assignment?
Okay. No, it is one subject assignment you are speaking, or
One submit only.
One subject assignment, it will come around 50 pages, sir. So we have around seven assignment to be written. I mean, overall, it will for every assignment it will take 40 to 50 pages.
Okay. Now then we will do like this. I'll speak to the coordinator today because we are saying around 40 to 50 MB. You're saying it's not possible to upload there. So let me make a Google form.
Yeah, that could be better. Otherwise, we are having a drive, Google Drive as well. But individually, somebody has to make efforts to download it. So
That's what. So for this today, let me speak with the coordinator and let you know you people. Tomorrow I'll inform.
Sure, sir.
Yeah.
Okay.
So if at all, it is also, if at all it is possible, one day in any day, stretching up to 31st May. So one day, if you also okay.
Now I'll speak today to the coordinator and I'll inform you tomorrow morning.
Yeah, please.
So
Please.
someday if you ask us to come and submit hard copy, even we'll be available to submit for that also, sir.
No, after May 3rd, we'll just see. Okay, if the relaxation is given, then you can travel, and even after May, if they ask us to come to the college, even we. Anyhow, you have time, no?
I'm having a time.
We'll make a decision.
Start the discussion. That's what. In the last moment, if at all they wanted to send us through mail only. So this is the limitation that the Google is not allowing.
Today I'll speak to the coordinator, and May 3rd, till May 3rd we will wait. So May 3rd onwards, if the relaxation is given and if the college people say faculties has to come, and you people, if you can manage to come over there to the college, you can submit it there itself, hard copy. Otherwise, we'll look for the alternative thing.
Sure, sure. Thank you so much.
Okay,
Thank you.
Thank you.
Thank you.
Yeah, thank you.
Thank you,
sir.
sir.
Yeah.